hidden in American workshops is an overlooked technology that has largely disappeared from public attention. As attention shifted toward battery-powered cars, American engineering groups continued, behind the scenes, reworking one of the automobile's oldest systems. Instead of accepting the familiar engine layout, they explored approaches once considered unrealistic. One concept eliminates traditional cylinder heads completely, along with conventional valves, while another abandons the crankshaft altogether, yet continues making power. Detroit also developed a compact four-cylinder, capable of carrying a family sedan for 106 miles, using energy comparable to 1 gallon of fuel. None of these concepts remained on drawing boards. They were not simply ideas searching for investment. Each technology became working machinery, installed inside actual vehicles, with some evaluated by the United States government. Several even reached everyday American customers in remarkably large volumes. This ranking examines 8 significant engine advances created in America, starting with the smaller ideas, before reaching one that challenged the whole industry. The technology occupying first place works differently from everything else in this ranking. It had already reached paying customers, with federal tests confirming that 106 result. Yet afterward, the manufacturer itself quietly stopped building it. But first place will have to wait. The story begins down at number 8, and each step upward brings something more surprising. Viewers who appreciate research like this can help the channel with a like, since detailed automotive research takes considerable time, and subscribe for future reports. Ahead are technologies, including one from Silicon Valley, where software provides the key engine innovation without requiring different hardware. Another design has even operated on vodka, plus a world record established abroad in spring 2026. That quickly attracted Detroit's attention. Number 8 is Tula Technologies' dynamic skip fire. Its first unusual quality is easy to explain. The important component is essentially invisible. Tula Technology operates from San Jose, California, yet its engineers did not create another engine design. They changed the instructions telling an engine what to do. General Motors later licensed this system under the name Dynamic Fuel Management. Its purpose centers on a familiar inefficiency. Consider a large V8 pickup traveling on level highway. While maintaining a steady pace, the truck uses just a small portion of its available engine output. Normally, however, every cylinder keeps operating, consuming fuel for output the vehicle does not need. Previous cylinder deactivation systems reduced this loss by shutting down the same 4 cylinders repeatedly. That approach resembles switching off half a home's lights and leaving that same group dark. Tula went further. Its strategy is closer to a drummer choosing each beat, one strike at a time, deciding instantly which ones sound and which stay quiet. Thousands of decisions every minute, without disturbing the rhythm. That behavior is controlled entirely through Tula's software. Every cylinder receives its own command during each revolution of the engine, either contributing combustion or staying inactive. As a result, the engine can run using almost any cylinder count, from a single cylinder through all 8, while revising that combination hundreds of times per second. Tula claims fuel consumption can fall by as much as 15%, and the concept progressed beyond controlled testing. Production vehicles began receiving the system in 2018, with the 1 millionth equipped vehicle rolling off an assembly line in November 2020. Applications include the Cadillac Escalade, Chevrolet Silverado, and Chevrolet Suburban, plus the GMC Sierra and GMC Yukon. Buyers do not select it as a separately priced option because manufacturers license the technology and integrate it directly into the vehicle. There is, however, an important limitation. It improves the efficiency of an inherently thirsty engine without rewriting the basic physics behind the way that engine consumes fuel. To do that, the engine itself needs a fundamental redesign, which is precisely what a Connecticut team attempted. Number 7 is Liquid Piston's X engine. Where the previous solution relies on software, this technology attacks the problem through hardware. Liquid Piston operates from Bloomfield, Connecticut. After being established in 2004 by a father and son, Nikolai and Alexander Shkolnik, following a second-place finish for their engine idea at a business contest held by the Massachusetts Institute of Technology. Their starting point was the rotary engine, an architecture closely associated with Mazda, but they effectively inverted its geometry. Traditionally, a triangular rotor moves within a curved chamber. Liquid piston flips that arrangement around. Here, the rotor takes on a figure-8 form, while operating inside a triangular housing. More importantly, its sealing elements remain in the housing, instead of traveling with the rotating component. That difference targets the difficult sealing and lubrication issues that undermined conventional rotary designs. For roughly 50 years, it is easier to lubricate something that stays stationary than trying to feed oil onto a rapidly spinning propeller. The physical package makes the result especially striking once the actual hardware is visible. One example, called the X Mini, displaces only 70 cubic centimeters and has a core mass of approximately 4 pounds, equivalent to around 1.8 kilos, close to the mass of a typical bag of sugar. Testing has also demonstrated an output of 3.5 horsepower. According to the company, these engines can be up to 30% more efficient than similar piston engines while operating on gasoline, propane, kerosene, and jet fuel, along with hydrogen and, during one test, vodka. The United States Army also funded development of a portable 10-kilowatt generator using this engine architecture, designed at roughly 1/4 of the size and mass of the generator, currently transported for field operations. Its current limitation is equally clear. No mass production automobile uses the engine today. Liquid piston currently targets generators and drones, applications where compact dimensions are especially valuable. The design demonstrates that old assumptions can change, but it is not yet powering family transportation. The next technology moves into a much larger category. Number 6 is a Cadis powers a post-piston engine. This is where the hardware becomes the kind of design capable of surprising experienced engineers. A Cadis Power is headquartered in San Diego, California, and was established in 2004 by late Walmart heir John Walton and physicist James Lemke. Their project brought back an engine configuration largely abandoned by engineers during the 1930s. Its operating principle is remarkably straightforward. A conventional engine places one piston in each cylinder, with a substantial cylinder head above it, and a valve system involving camshafts, springs, and valves. This layout works differently. 2 pistons occupy each cylinder and face inward, with combustion taking place directly between them. Ignition then forces both pistons away from each other, driving separate crankshafts positioned at opposite ends. Since the cylinder does not require a conventional top, the cylinder head disappears, along with valves and the complete valve train. That eliminates hundreds of individual components. The combustion space also becomes long and narrow instead of using a broad, shallow chamber, reducing the amount of heat transferred into surrounding metal. Its largest highlighted version displaces 10.6 liters, using 3 cylinders paired with 6 pistons, and delivering 450 horsepower with 1,150 pound-feet of torque, equal to approximately 2,273 Newton-meters. Its peak brake thermal efficiency rises beyond 49%, a remarkable level for an engine intended for road use. Real-world evidence came from highway operation. A Cadis fitted the design inside a Peterbilt 579 tractor, operated by Walmart's California fleet, where it remained in service for over 6 months. Depending on the route, fuel use dropped between 4 and 21%. Against the strongest conventional engine in its category, the engine also satisfied California's demanding 2027 emissions threshold of 0.02 grams per brake horsepower hour. A more compact version was developed as well, using 2.7 liters to produce 270 horsepower, with the target of allowing a full-size pickup to achieve 37 miles per gallon. That performance raises an obvious question for the industry. Why has this architecture not reached trucks everywhere? The reason is practical. Today's worldwide automotive supply network, from manufacturing plants and tooling to trained technicians, has evolved around traditional engine architecture. Replacing that infrastructure requires billions of dollars. Efficiency by itself rarely transforms an industry. A larger incentive is usually required, and one national project pursued exactly that goal. Number 5 is Cummins' 55% Supertruck engine program. Its importance centers on 1. Critical measurement used throughout engine development. Brake thermal efficiency. This figure describes how much fuel energy is ultimately converted into useful movement. Some context makes that number clearer. In a typical gasoline-powered passenger vehicle, roughly 1/4 to 1/3 of its fuel energy is transformed into forward motion. Most of the remainder escapes as heat through cooling hardware in the exhaust system. So during every fuel stop, much of the purchased energy ultimately heats the air. By 2010, leading heavy-duty diesels reached roughly 43%. The United States Department of Energy then introduced its Supertruck initiative, with Columbus-based engine manufacturer Cummins joining the effort from its beginning. During a cold January night in 2021, inside a test cell, Cummins achieved 55% brake thermal efficiency, using a diesel power plant, combined with a waste heat recovery system. The Department of Energy later formally acknowledged that result. During the same year, waste heat recovery adds another layer to the process. Alongside the main engine sits a smaller secondary power system designed to collect energy from extremely hot exhaust and convert that heat into additional useful work. In effect, it works like a compact steam plant attached to the exhaust. More than 200 people at Cummins supported a central group of 25 engineers who advanced toward the target through small improvements. Cummins also spent years collaborating with Tula on adapting the company's system for diesel skip-fire operation. Testing showed nitrogen oxide emissions falling by 74% when the technology operated on a Cummins X15, while carbon dioxide output declined by 5%. There is an important qualification. The 55% result represented a peak efficiency operating point, achieved with a large engine inside a test cell, using equipment that increases both expense and complexity. It demonstrates the upper boundary of physical efficiency, rather than a dealership-ready specification. Even so, the achievement pushed the benchmark higher. Another California company then questioned whether a crankshaft was necessary in the first place. Number 4 is Mainspring Energy's linear generator. Its architecture challenges the familiar image of an engine entirely. Mainspring Energy began in Menlo Park in 2010, created by a group of 3 Stanford engineers. Their machine operates without any crankshaft, without connecting rods, and without rotating components along its power path. Instead, the system contains 2 oscillators, with magnets at their ends. These components travel repeatedly along a straight path, powered by a low-temperature chemical reaction without flame. As the magnets move rapidly alongside electrical coils, electric current is produced directly. No rotational motion needs conversion, and no gearbox is required. The motion stays completely linear. The moving element travels between 2 magnetic springs, producing electricity with every stroke. Because combustion occurs at comparatively low temperature, without an open flame, nitrogen oxide output from the machine remains extremely low, with no particulate matter produced. Those characteristics allow installations in locations where traditional generator equipment may not be suitable. Its reaction is also managed by the control system through electronics instead of mechanical hardware. That enables rapid changes between different fuel types, including natural gas and propane, as well as biogas or hydrogen without conversion work. Individual installations range from 250 kilowatts to capacities exceeding 100 megawatts. Commercial shipments started during 2020. Then, in October 2024, the Department of Energy committed $87 million to support a new manufacturing facility located in Allegheny County, Pennsylvania. The following year, in 2025, Mainspring secured $258 million through another financing round, including Amazon's Climate Pledge Fund. Meanwhile, National Grid announced an installation at its Northport facility in New York, designed to operate on 100% hydrogen, but its automotive limitation remains significant. These generators currently serve data centers, hospitals, and vehicle charging locations. They are not installed in passenger cars. Even so, the technology illustrates an important transition that connects directly with the next entries. The engine's role is beginning to change, moving away from wheel drive toward electricity generation. That transition helps explain the 3 highest-ranked technologies still to come. Before reaching those final 3, there is another question worth examining. Why are these developments arriving today, instead of appearing 4 decades earlier? Part of the explanation is an engineering conflict that persisted for generations. Greater engine efficiency generally requires compressing the air-fuel mixture harder before combustion. Push compression too far, and uncontrolled ignition can occur prematurely, placing destructive loads on the engine. That constraint restricted efficiency for many generations. There was another issue. Engines approach peak efficiency under substantial load, yet everyday driving rarely keeps them there. During ordinary stop-and-go traffic, a large engine often provides only modest output, where efficiency can deteriorate dramatically. 4 developments eventually changed that equation. The first was fuel injection, capable of operating at exceptionally high pressures, breaking fuel into extremely fine droplets. For cleaner combustion under very high compression, advanced valve timing also allows an engine to use less effective compression than expansion, extracting additional energy during combustion. Then electric motors and power electronics became affordable, lightweight and dependable enough for direct wheel drive. Battery technology followed, becoming inexpensive enough to provide an energy buffer, removing the need for engine output to follow accelerator input. Instead, the engine can remain near one ideal operating point, running steadily where efficiency is highest, while electric motors and the battery respond to driving needs. That separation changes the entire efficiency equation. Then, during April 2026, the urgency surrounding this approach became much clearer. A Chinese manufacturer, Geely, certified thermal efficiency at 48.41% from one of its hybrid engines, with Guinness World Records confirming the measured run. The result was 2.22 liters per 100 kilometers, from an M Grand sedan, equivalent to approximately 106 miles per gallon. Most of that test took place on highways. For context, Toyota's Prius recorded 92.9 miles per gallon during its separate efficiency test. That certification pushed the number 106 into automotive headlines worldwide. This was controlled testing rather than normal driving, so that distinction remains important. Yet, one important detail received far less attention. An American vehicle had already received the same figure from federal testing. Over 10 years earlier, before Detroit abandoned the concept. Number 3 is Scout Motors' harvester system. At this point, the focus moves beyond research facilities toward customers. Scout Motors is constructing a factory in Blythewood, South Carolina, for 2 upcoming models, the Traveler Sport Utility and Terra pickup. More revealing than their styling is the powertrain strategy behind both vehicles. The harvester configuration combines a battery rated at roughly 60 to 70 kilowatt-hours with a gasoline engine disconnected from the wheels. That engine serves only as an electricity generator. Battery power provides approximately 150 miles of travel, equivalent to about 241 kilometers. Once gasoline generation becomes necessary, combined range exceeds 500 miles or roughly 805 kilometers. The battery uses lithium iron phosphate chemistry, a lower cost and more durable chemistry than alternatives, while pricing is expected to begin below $60,000. The most revealing figure, however, does not come from the specification sheet. Chief Executive Scott Keogh reported that about 85% of reservation holders selected the range extended model instead of the fully electric version. Those deposits provide a clear signal from American customers, and Detroit's executives certainly noticed the result. There is still one obvious limitation. Production remains scheduled for 2027, and customer vehicles have not reached drivers yet. Another truck is expected to arrive ahead of it. Number 2 is the Ram 15 RAV. Here the same concept moves toward production hardware. Originally introduced under the Ram Charger name, the truck is now badged Ram 15 RAV. A production-ready version appeared during the 2026 Detroit Auto Show, with manufacturing currently scheduled for Michigan's Sterling Heights assembly plant during the second half of this year. As a 2027 model, it applies the same basic architecture on a full-size platform. A 92 kilowatt-hour battery is mounted between the frame rails, supplying a 250 kilowatt front motor and another 248 kilowatt drive unit at the rear, together producing 647 horsepower, along with 610 pound-feet of torque, or approximately 827 Newton meters. Electric-only driving covers roughly 145 miles, equal to 233 kilometers. After the 3.6-liter V6 begins operating as a generator, combined range increases to approximately 690 miles, which equals about 1,110 kilometers. Maximum towing capability reaches 14,000 pounds, or approximately 6,350 kilograms. One broader detail shows just how far the industry's strategy has shifted. Stellantis had initially planned a battery-only Ram pickup, but dropped that project in favor of this approach. Ford has also publicly moved towards similar architecture. General Motors currently offers no comparable vehicle in the United States, but says plug-in powertrains will arrive during 2027. The direction of the industry has clearly changed. What makes that reversal especially unusual is that none of these manufacturers created the concept. They are revisiting technology America previously offered. Number one is the Chevrolet Volt. More specifically, General Motors' Volt system. This is the technology behind the result, introduced near the beginning of the report. The second-generation Chevrolet Volt received an official United States Environmental Protection Agency rating of 106 miles per gallon equivalent, combined rather than a marketing estimate or an internal company claim. It was federally rated and displayed directly on Chevrolet showroom window stickers. That happened approximately a decade ago. Its underlying architecture closely resembles the solution manufacturers are now returning to. An 18.4 kilowatt-hour battery provided electric propulsion for the first 53 miles, or approximately 85 kilometers without gasoline. Once battery energy dropped, a 1.5-liter, four-cylinder engine producing 101 horsepower started operating to generate electricity, bringing combined range up to 420 miles, or roughly 676 kilometers. The gasoline engine used regular unleaded and achieved 42 miles per gallon. While it was operating, Generation 2 also removed 246 pounds, around 112 kilo, while reducing the pack to 192 cells, from 288 cells in the previous model. Pricing began at $33,195 before incentives. One road test made that efficiency easier to understand. A reviewer traveled 106 miles in the Volt, while consuming exactly 1 gallon of gasoline, plus approximately $1.50 worth of household electricity. That placed the total trip expense at roughly $3.50. General Motors estimated that 90% of Volt trips could avoid gasoline completely. Despite that, production ended in 2019. Its concept arrived before broader market demand, while its price remained high relative to size, and much of the automotive industry believed battery-only vehicles represented the final destination. Production tooling disappeared and engineering teams moved on. 7 years afterward, a Chinese manufacturer established a world record using a broadly similar powertrain philosophy. Meanwhile, American buyers placed reservations at roughly a 5-to-1 preference for the range, extended version of a pickup not yet available. Ram and Scout, along with Jeep and Ford, plus Hyundai, are now pursuing versions of this same architecture that Detroit once placed into production, sold to customers, and later discontinued. That is the reversal. The disruption comes less from invention than from realizing that a workable answer had already existed. Across these 8 technologies, one system selectively disables combustion, another reverses rotary geometry, and another places 2 pistons inside one headless cylinder. One diesel recovers useful energy from exhaust heat, while another generator eliminates the crankshaft. Then 3 vehicles apply a different role for combustion, removing direct wheel drive, and using the engine primarily to generate current in America. Together, these examples point toward one conclusion. Combustion engine development has not stopped. Instead, engineers are changing its internal architecture. Vehicles emerging through the rest of this decade could consume far less fuel than today's conventional